Okay, I intend to prove the double slit experiment doesn't work out the way they say. It's not a particle and a wave, it's a particle. There is no wave other than the fact that it's spinning, and if you look at a spinning particle, from the side, it's a wave, yes. But as it's going forward, it's a particle, and it spins through the slit this way. So some of it goes this way to that side, some of it comes under and goes this way to that side. Now why in the full spectrum is there blue only here, and then you go into your greens, and then you go into your reds out further? Why is that? Well, I can explain it. All right, this is the reason that the red has no power to speak of. It's just one little box like this. It has an up and it has a down. A positron and an electron. That's it. Then you have a couple of these together, you go into your green where it has some power. And then you put another couple of these together, you get into your blue where it's starting to get devastating. The red can't really do anything. It cannot drive electrons. That can drive electrons on the higher end, and this drives electrons on every single bit of it. You just drop it on like a little raindrop, and it's so heavy that it pushes electrons out. Then you go more bigger pieces, and you're heavier in UV and X-rays and gamma rays and all your dangerous rays out at the very end of the spectrum because they're heavy. That's the problem. They're heavy. Now, I'm going to show you why I can show this. And they spin faster. There's an angular momentum, and there is an amount of particles. The amount of particles dictates the angular momentum. The angular momentum and obviously the forward speed dictates the impact power. That's very impactful. Nope, nothing. All right, I'm going to get deep into this as we go forward into this particle physics. But let's just say you have two particles, okay? You have a red, which is one single set of an electron and a positron. And you have a blue, which is a bunch together, which is, it's heavier. Of course, this is a smaller looking diameter, but it would be bigger. It would be a big, heavy wire. Big thick wire, and it would be spinning fast like this, and when it approached the slit, it could come here, it could come here, it could come here, because the slit is only here. So if it hits spinning this way, it might go up over this way, but it can only go to it's only this big around. It can't get way out here. It can get mostly through the center, and then it gets here, but it can't get way out over there. Well, what about this? Well, this is a whole different issue, because this one hits way over here, it comes way out to here. And they're even bigger. They're huge, these things. So when it hits, it can go way out and way out. Now, I just did a little drawing of it to make it a little more simple. But this is what we're looking at right there. It's as simple as this. And I'm going to call this electron flood spring theory. Because these springs are nothing more than what happens to the photon when it crashes into something. It's like a beach ball. It goes boing, and that excites it, and that pushes. It's the push of them. You push two magnets together, you can feel it. You feel like you're pushing two beach balls together. Identical. It's a spring. Now, photons spin, and just like I showed you, spin in these little, just like this, and they spin forward, and it's on a right-hand rule, so it spins this way. And I got pictures of that too. I got pictures of everything I'm going to show you in a minute. I'm going to show you exactly what, I'm going to show you these photons. I'm going to show you how they come out and how they create Higgs bosons. Alright, so here we got photons eject from excited matter due to collisions and magnetic repulsion, bounce inside of them. You force electricity into a bunch of matter, and it's going to shoot electrons out. Simple as that. Tight spin means more energy from the angular momentum, less diameter, and more power. That's the blue. Same particle, the diameter, the thickness of the particle is the same, but it spins tighter, and it's going a lot more cycles per second. This is less cycles per second, and but the same particle, so it's not smashing into something quite as hard. And this has very few cycles per second. Well, it actually has none. It's like so long that it takes a long time before one of these makes a wave. Now, so what happens to the slit? There's a slit. Oops, I gotta sneeze. Okay, a minute ago I made a mistake. I said they are the same particle. They are not the same particle. This is a very light particle, this is a heavier particle, and this is heavier still. They spin faster, this one does, And that one spins faster than the red. The red spins slow. That's why they have these long frequencies. But they are bigger particles, littlest, which it's like a ping pong ball. You throw that, nothing's going to go. You cannot knock an electron away. I don't care how hard you throw the ping pong ball. You drop it, nothing. You throw it at 1,000,000 miles an hour, nothing, because it cannot displace an electron. Different story. Displaces one every time. You drop it like a raindrop. Boop, electron goes away because it's huge. It's like dropping a cannonball. All right, so I'm sorry I made that mistake. I'll never do it again, I promise. Whew, it's good to get in here to sneeze. All right, here we go. So we got our three major hitters here. And that's all there is. So you got you got your basic photon, your middle photon, and your hard photon. Above that is your heavy particles. They're all particles. And the only reason that they interact the way they interact in the Fraunhofer lines is because they have certain chunks to them. They're not all the same particle. They're the same particle, but they're combinations of the same particle in chunks. And that's what happens in a nuclear bomb. You know, it's not neutrons flying all over the place. There is no neutrons, first of all. They are chunks of protons. They are chunks of Bohr magnets, 20, 30, 40, 50 of them together instead of 1, 2, or 3. Now, here's what happens. The red spins big. The green a little less, the blue real tight. So the blue comes in here, it's only got this much of a wave front to it. So it can only spin and only can catch over here, and of course the bottom goes that way, the top goes this way. Same thing with the green, a little further, and the red a little further. That's why they mix and make reds and yellows and blues and greens and all that stuff in the full spectrum. And of course, here's what you're looking at coming at the slit. The reds are way out here, the blues, greens are down, and the blues are right in the center. The particle is that, which I showed you before, and I will show you again, actual particle in midair. First thing you have to understand is that light comes out all just in clusters. That's a red laser, and these are the spinning, pulsing little particles. This is, I can't get any more proof than this. This is the spinning light particle. You see this? As that light spins, the slit is right here. Right? The slit is right here. So what's going to happen? It's going to hit here, here, here. It's going to hit all over the place. But the slit is the only place it can go through. So most of it's going to be here, 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 right in this area that's going through. So therefore, the main bulk of it will hit in the center. There is where our brightest light is. So what else is going to happen? It may hit way over here. It's going to go out here. Or hit way over here, way over. These right there, those are the patterns. Zip, 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 zip. Those are the patterns. Now, why are we seeing them here? This is the back wall. Okay, the slit is way up here. And we came through it, and this is the back wall, and we are seeing the patterns. So, therefore, the slit is here. There's a solid mass here that this is blocked. It can't hit there, so we get nothing here. But once it hits the slit, well, what happens at the bottom? Same thing. We got a mass here. It can't hit. It comes around, nothing here, but as soon as it can dive under, we catch it on this side. As simple as that, spinning light. All right, I'm going to just run through these real quick because I've gone through these so many times, and they're all up on my channel, Mudfossil University. Now, that's just a red laser, pulse red laser light, and it's accelerating the particles that are in the air, which are ether. This is the accelerated wave. And that is the particle that emits from there. You know, there's a zillion of them, but that's what you're seeing them. And they're cascading into this venturi, crushing into each other's regions because they own large regions around their nuclear self. And as they come through here, they are repelling each other like springs, like beach balls crushed together. And they're all pushed apart. And we see these interference patterns I explained, I hope, well. Now, this is the Higgs fields that come out from the other side after. This is Cherenkov radiation. It is high speed. We can see it accelerated. There's no question accelerated. It is higher speed than is allowed in this medium. That's the definition of Cherenkov radiation. It came out of this acceleration and crashed into the standard air that it's not meant to be in because it's ahead of it. And it created these particles, spinning little particles, which are called bosons. They created the spinning little polarized fields that surrounded that charged particle. That is the definition of a Higgs field and a Higgs particle and a boson and all that stuff. So I don't think I'm outside of my boundaries talking about this. This is something that nobody's got a clue about. Right there, you see? That's a new particle. What happened when the Higgs bosons up there on the right came out of here, there was one that was reverse spinning, crashed into this part, and ended up with this, whatever that is. We're going to go into this very deeply. I have a lot of stuff on this. And and what I want to talk about right now is Rodney Warren. I always say his name because he's the one that came up with this Venturi. It was quite by accident. He has nothing to do with the atomic theory whatsoever. He's not interested in that at all. He was interested in seeing if he could find things in light that everybody was overlooking, and he did. So if anybody says, oh, we're looking for things in light, you talk to Rodney Warren, because that is the guy that can help you, my friend. If you think you got to go to some PhD that's going to tell you how there's things living in light, no. You talk to Rodney Warren, he'll show you what's going on in light. That is the guy you want to talk to. Now, I worked with him for, it's got to be well over a year, and he just worked over tirelessly. He didn't really have any, like I say, no interest whatsoever in the atomic part. But I'm seeing things, I'm saying, Rodney, will you do this, please, please, please? And he did everything I asked. I had thousands of pictures. I'm going to do a tribute to Rodney on this because he's the guy that really deserves a huge amount of credit. All right? And he will never get it unless somebody speaks up for him. All right, anyway, that's the particle. I told you, I believe that is the red photon. All right? It obviously is two dipoles, one up, one down. What can I say? That is what they asked for. That's a positron and an electron. As far as I'm concerned, this case is really closed. That's the particle of boson coming out of there at a high speed, spinning to the right, drifting to the left, open, compressing, obviously slowing. You know, this whole thing about Einstein and light can't speed up and slow down, that's just not right. So and none of it's right. And I'll show you that there's three particles. Another friend of mine, these are just normal people. But you have to put the things together. You can't just say to somebody, here, I'm going to teach you what everything's about, and you just repeat what I say. No. You say, well, look at this. And he says, well, look what I found. I said, whoa, wow, what did you find? And I say, ooh, will you do this? And they did. They do it. Let me show you something Ren sent me. I don't see how can it get any better than this. That's the Higgs field of all the particles together in white light, and it is white. Obviously, that's what you expect. And what is it made of? It's made of these three primary particles. Blue, green, red. Blue, green, red. Blue, green, red, all the way down. Why are they separated? Ren's created a half Venturi. What he did, all he did is put his thumb up like this. Took a picture into the sunlight. Well, the sunlight is full spectrum. It actually cascaded off his fingertip and did the same spin that we see through a Venturi, only this is a half a Venturi. And the rest just flowed through here as we would expect the Higgs to do. As far as I'm concerned, I can't see how anybody can contest this particular set of circumstances to show all of these things. And now we are in the neutrino range, my friends. These are not the particles that CERN works with. CERN says these are impossible to see. I say you can see them, and you go out right now and see them yourself. All right, CERN works in the heavier particles. As I said, as it goes up in the weights, they get to be devastating particles. And these are the things that hurt you: X-rays, gamma rays. All right, now, and they come in just heavy. Now, the electron neutrino comes in faster. Well, this comes in faster than it should too. It's Cherenkov. Anytime you get Cherenkov radiation, it's faster than it's, see right here, Cherenkov radiation from an electron shower produced by an electron neutrino event produces multiple cones, therefore a diffused ring in the detector array. Well, that's what we have, and we're showing that. It's quite obvious. Now, the electron neutrino is the tiniest particle supposedly there is. Electrons supposed to be the littlest bittiest part. They don't even hardly care. They think they can't see them. They think they just really almost don't exist as far as weight goes. And they certainly exist. And they certainly, at least half of them can be seen. I mean, at least two of them together can be seen, up and down. And I saw a particle come off of those, and you did too. I can't explain. I'm going to show you how it happened. All right, here's the proof that, as far as I'm concerned, is absolute proof. The beauty of working with Rodney was that we were just sort of winging it. Now, he would send me things like this. I would look at this for literally, well, I've been looking at them for years. It's been over 3 years I've been looking at these. Now, you see the spin? He didn't have it dead through the center of the Venturi. Right, which is perfect, because I know this for a fact, because you see how far it trails off here, and you can see there's a spin here and a spin here. This is not the same particle. He's got it on an uptick going this way, and on, let's see, I think it would be this side. So he's got it coming up here. So we're just getting this real little spot here, and then it comes way up here, because he's got it facing out in this direction. Now, he did this a number of times, which was fabulous, absolutely fabulous, because he was showing me things that you will never see, because they'll set up the experiment. Oh, no, you got to get it to the right. Forget this. Oh, no, you see, you messed it up. Well, what happened when you messed it up? That's the stuff I go for. It's like when people send me Mudfossil stuff. They send me a beautiful shot. Oh, look what it is. No, I want to see where it broke. I want to see where the blood vessels are. I want to see where the anatomy shows up, not some, like, thing that looks like something, because that is nothing. Until you can show me the makeup of it, the particles, the physical architecture that cannot be denied, like this, then it's really nothing. But this is something. We do have the same things in green as well. They're a little more high powered. You can see all those intense little pulses. I think you can see them. Okay, here's another one that was shot off angle. You see these particle beams coming out of here? This one here is shown. That is actually the particle. And these are the fields surrounding the particle as it spins. And these are the pulsating particles that are affected by the magnetism of this spinning photon. It's got the plus and the minus. Plus and the minus is spinning around like crazy. And the North Pole will always be there. That's the right-hand rule. The North Pole is that way. The spin will be this way. So this is spinning here, heading out that way. And we do have the green particles as well as the red ones. They look the same. That's the only thing that worries me, because I haven't seen the blue ones, but the green can only be back-to-back is all I can think, and the red is just one of those. There's still a little work to do, but I think this is getting pretty close. I think I made my case about these particles. Now, here's the puzzler, though. If these things hit and emit electrons, what happens to the positron? Where does that go? This is something I'm sort of puzzling around in my mind, the interaction of the actual particles crushing into each other. What causes the glow, first of all? I see that as possible. I got some ideas on that. Anyway, we'll go into that later. Okay, and one more thing. I was watching the History Channel. Michael Dennin here, PhD, is professor of physics and astronomy at UC Irvine. Seems like a very nice guy. They're trying to figure out what happened to the excess matter that's supposed to be in the universe, and it's nothing more than the light particles on the way to concuss with something. They don't do anything until they hit something. If a guy is floating around out there and he gets hit with him, he heats up, burns up in space. If he's down in here, sooner or later it concusses with the atmosphere of the Earth, and it is pulled to Earth magnetically, because Earth is a positive puller of particles, of negative particles. These photons crash into the upper magnetosphere, creating electrons. The electrons become the ionosphere. The ionosphere is a negative layer surrounding the Earth. Between that and the Earth is a capacitive area, really. It comes and goes. sucking up electrons and releasing them. You get lightning, you get this, you get static, all that stuff. And the magnetic stripes in the Earth, there's magnetic stripes in the ocean. That's what's pulsing the Earth into a magnetic field as it spins in the ether, which is nothing more than the electrons that surround it, just like you would have magnets surrounding coils of wire, and that makes a motor or a generator. It depends which way you're turning it. So we need to look at this as a machine, really, is what it is. We are a generator or a motor. I'm not even sure. I haven't really looked. We're really a generator. We're spinning into the particles. They push against our magnetic stripes, which are negative lines, and it pulses just like into a wire, and that creates the north and south poles. And I'm going to tell you another thing. I think the north and south pole, there will be a hot spot in there because there's going to be current flowing. That's a current flow. And they say it's 100,000 or 100 million amperes. I can't remember what it was. But this is what creates your aurora borealis and the southern lights, is because of this enormous amount of electronic interaction at these particular poles. It's where the fields collapse on themselves. And when you get a ton of solar radiation is when you see these aurora borealis. They know when they're going to happen. They tell you, oh, tomorrow's going to be a big one. Well, that's because they know there was sunspots on the sun ejecting tons of electrons which are going to interact with these fields and make them glow. It's as simple as that. It's really not as complex as they're making it, trust me.